The Wolff-Kisher reduction is actually a two-step synthesis converting a ketone to an alkane. So it's essentially a reduction of the carbonyl carbon all the way down to a methylene. We've seen this process before. We've seen the reduction of benzylic carbonyls using the Clemmensen reduction. That was introduced in chapter 18. And we've also seen the reduction of a thioacetal using Raney nickel. That would be under acidic conditions. So that's the conversion of a ketone to a thioacetal, and then the reduction using Raney nickel. You can find that in another part of this chapter, actually. So this reduction will undergo, will utilize conditions that are basic. And so that's different from the other reductions that we've seen. The Clemmensen reduction using a metal and acid, that again only works on the benzylic carbon, and then the Raney nickel, which works on any carbonyl, doesn't have to be benzylic, however it occurs under acidic conditions. So if you had a acid sensitive substrate, you would not want to use acidic conditions. So this would be a way to reduce a carbonyl to a alkane, or at least the carbonyl carbon down to a methylene, utilizing basic conditions. So again, it's two steps. The first step is the conversion of a ketone to what's called a hydrazone, and that utilizes a reagent called hydrazine. But if you notice, the reaction is really just conversion of this carbonyl, or the CO double bond, to a carbon-nitrogen double bond. So it's sort of analogous to the formation of an imine from a carbonyl. And the mechanism is the exact same. The only difference is in imine formation, we would be utilizing a primary amine, and in hydrazone formation, we're utilizing hydrazine. So essentially, if we were doing imine formation, one of these NH2 groups would just be an R group. Then this would be an R group, and we would call this an imine. But since it's an NH2 group, the entire thing is called a hydrazone. But again, the mechanism is exactly analogous to imine formation. And then the second step will be an elimination reaction. We're going to look at the mechanism of the second step, because again, the first step is just imine formation, which there's already a video for that. Okay, so starting from hydrazone, we're going to look at what happens under basic conditions. So I'm going to draw out hydrazone, all the important lone pairs. And then again, the conditions are potassium hydroxide, water, and heat. So we have some hydroxide. And whenever you're under strong base conditions, you're likely to be deprotonating the reactant. And where are we likely to deprotonate? Probably one of these hydrogens attached to the nitrogen. So let's see what that forms. So we've just done a proton transfer. That nitrogen will now be negatively charged, and will form some water from that proton transfer as well. So this substrate is resonance stabilized. So we'll go ahead and draw the resonance contributor. So this is an allylic lone pair, so we can just do the allylic lone pair pattern. And this generates our other contributor. Okay, so now that we've shown that part of the negative charge in the lone pair exists on this carbon. It's essentially a carb anion. And so that's pretty basic. So it will actually pick up a proton pretty readily from water. So just another proton transfer. And that gets us here. Okay, we're going to use a second equivalent of hydroxide. So we actually need at least 2 equivalents in this reaction. And again, it will deprotonate the hydrogen on the nitrogen. And then essentially we can use that extra electron pair on the nitrogen to form a pi bond and kick out the carbanion in an elimination reaction. So then we've formed nitrogen gas, which will of course bubble out of solution, and a carbanion, which will be very basic. And so any water present would definitely protonate that. So we'll show one final proton transfer. To get to the product. So the product would just be a cyclohexane in this case, and then we've regenerated some hydroxide here. Okay, so a lot of these steps are reversible, but the one that's the least reversible would be the step where we expel nitrogen gas. That if that's allowed to bubble out of solution, that will be gone, and so that step would be unlikely to go back. So that will drive the equilibrium